Good evening, everyone, and hello. My name is Dr. Keith Grimes, and I am pleased to be presenting to you today. I'm sorry that I'm not there in person, but I hope this video presentation will be helpful for you. I'll be speaking about generative AI and what part it will play in radiology. So thank you to the chairman and the committee of this forum. And with that, we will get started. Just by way of brief introduction, this is me. My name's Keith Grimes. I'm a general practitioner in the UK, and I'm the founder of Curistica, which is an innovation consultancy. My interests are broad, including a clinical interest in urgent care, but I've always been very interested in technology, having roles within industry and also the National Health Service, and role in leadership too. And I have some academic affiliations listed at the bottom of this slide here. Today, I'm going to be talking about generative AI and radiology. Now, you'll have been hearing some other talks about artificial intelligence, so you may have heard some of these things covered before, but I suppose what's really important when we talk about radiology is that radiology and AI appear to be the perfect fit. So what do I mean by this? Well, they're a perfect match because radiology is such an image-rich environment. It is a data-rich environment, and there's a very high demand on pattern recognition within this as well. This is something that artificial intelligence is already very, very good at. And of course, in the clinical world, there's a very high demand on radiology services and a rather constrained supply. Wherever you are in the world, there appear to be fewer radiologists than there is demand for the care. And this is reflected in all the research, but also in the commercial side of things. There's many, many papers and many real-world products blending artificial intelligence into radiology. And one just has to look at the FDA submissions, the submissions in the US, with 85% of clinical AI products actually being applied within radiology. Just in the last year, 882 AI products. Of that, 76% roughly were in radiology. Now, what's interesting about this, and I come back to this, is that only a small number of these are actually approved in Medicare and Medicaid settings. So even though a large number of applications have been developed, in terms of those that required supported healthcare, actually only a small number of them are being reimbursed, which is limiting their impact. Now, I'm a UK-based clinician, and in the UK, there's been a great interest in artificial intelligence, and we're seeing quite a lot of real-world applications. So in a recent College of Radiologists survey, 50% of the departments across the UK are using artificial intelligence, and we're seeing rapid adoption of things such as rapid AI, brainomics, and Viz, as supported in the NICE guidelines DG52. But at the same time, we're taking quite a critical view of this and looking at artificial intelligence for analyzing chest x-rays for cancer of the lung. The recommendation was these would be used in research purposes. So this is AI in general. What about generative AI? Well, briefly, I'm going to go through the setup for generative AI. So what is generative AI? It's useful to place this in the large family of artificial intelligence. So artificial intelligence broadly describes any system that performs tasks that might otherwise require human intelligence. And as we take this very large set and move closer or further in, we have within this machine learning, which are models and algorithms that allow computers to learn from data, particularly large data, and make useful predictions and decisions from this. And within this, one of the architectures is neural networks and deep learning, models that are based on the modeling within the brain, digital neurons, so to speak, again, capable of doing unsupervised learning from large data. But at this point, it starts to get difficult to explain why decisions are being made, the so-called black box phenomenon. And then within this deep learning set, we have generative AI. So models will generally make predictions and decisions from data. Generative AI, from these patterns, goes back out the way and generates data. And that could be in many forms. It can be in text, images, sound, video, whatever you like. Today, we're going to be speaking specifically about text, and that is large language models, which fit within this small set. So what is a large language model? Well, a large language model is very simply a type of generative AI, a deep learning model that works specifically on language and text. And this is based on something called the transformer model. And for those that are interested or maybe haven't seen, this is back in 2017, this seminal paper published here, as you can see on the screen, looked at this model, which allowed these models to focus very specifically on the most important parts of the text that it's being trained on or making inference from. At its simplest, what this does is it allows the model to look at the relationship between words, what they mean, and the context, where they are in relation to each other. So at its very simplest, a large language model takes a text input, breaks it into tokens forms that can be analyzed by the machine, and then repeatedly predicts the next token iteratively until it predicts that it should stop. At that point, it converts it back to human readable text. And that, at its simplest, is a large language model. So when we talk about large language models, what do we mean by large? Well, large can refer to two aspects here. It can be a large number of parameters, these digital neurons. And by way of comparison, as we show you this, the human brain has about 100 billion neurons, about over 100 trillion synapses or connections. And this is roughly equivalent to parameters in these models. And then we also mean large data, because you have to train on a large amount of data. And to help you understand how much data, we're going to help with an analogy. If you imagine a single sheet of A4 paper contains around about 500 words or 650 tokens. And so if you stacked up 100 of those pages, it would be about 1 centimeter high. So large language models. If we look at the output of OpenAI, one of the large companies working in this area, if we look back to June 2018, their first iteration, GPT-1, Generative Pre-trained Transformer, had around 120 million parameters. Now, in animal equivalents, that's the same about as a fruit fly in terms of synapses. And it was trained on 1.3 billion tokens. Now, using that analogy, using that stack of paper analogy, that amount of data would be the equivalent to around about 200 meters tall. So that's about a quarter of the height of the Burj Khalifa. GPT-2, which followed a few months later, at that point, they moved up to 8 billion parameters, 1.5 billion parameters, pardon me. That's the equivalent of about 1.5 honeybees in terms of synapses or connections. That was trained on 8 billion tokens, a collection from the internet and a book corpus. And that is approximately 1.23 kilometers high by that. Again, imagine the Burj Khalifa, 1.5 times taller than that. That is a physical representation of what the training data might look like. And then we moved on to GPT-3. And GPT-3 in June 2020 had 175 billion parameters. Now, the human brain is larger than that, about 0.2% of that size, trained on 500 billion tokens. Now, by that same analogy, if you were to represent that as physical paper, that would be a stack of paper nearly 80 kilometers high. That's many times higher than the commercial airliners that we fly to and fro. And then the most performant model we have, GPT-4. Now, we haven't got very exact figures on this because they haven't been published, but the understanding is it's around about 1.8 trillion parameters, 2% of what might be the synapse volume of the human brain, and 13 trillion tokens, a phenomenal amount of data that would equate to being about 2,000 kilometers high. That would be the equivalent to the border between low and middle Earth orbit. It's an incredible amount of data taken from many sources on the internet across many different languages. And as a result of that, these large language models learn patterns that allow them to do very useful things. So what sort of things can they do? Well, first of all, you need to know how to build them. And broadly speaking, when you're building a large language model, you have to load it with knowledge, you have to align it, and you have to align it to human preferences. The first part is pre-training. And in pre-training, you take one of these models, which is randomly initialized or taken from a previous model, and then taking this enormous amount of data, you train it to predict the next word and then correct if it gets it wrong. And you do this over many months, costing tens and hundreds of millions of dollars. And at the end of that, you have a foundation model, a model that's very good completing documents. Now, that may be useful, but you need to align it to perform something useful. Now, this process of alignment is called supervised fine-tuning. You take this base model, and then you give it examples of inputs and outputs, created often by humans to certain rules, but also by machines as well. And you train it again. And at this point, it's learning how to perform tasks, answer questions, summarize data. And at the end of this, you have a supervised, fine-tuned model that you have to then tune further using a process called reinforcement learning with human feedback. That has 2 stages. This model will then, with certain curated inputs, produce multiple outputs, and humans will rate the output. That will train the model, but also train a second model, which allows us to do it at scale. And at the end of all of this, you have a reinforced learned model, such that you might use in one of the models that you may be aware of using. At the end of this, so you've got this trained model. What are its strengths? What are the weaknesses? And what are the risks? So we start with the strengths. And of course, Hopefully, many of you have used large language models or forms of generative AI, so you'll know that these models do a very good job of expanding, going from a small amount of information to a large amount of information. And this could be, for example, answering questions. You put in a question or a task and it creates a large output. What about summarization? It's the opposite, giving it a large amount of information. For example, you can imagine a radiology report and then turning it into a small summarized information, or potentially pulling out some of the clinical codes. And it does an excellent job of translating from one language to another, or from one level of language, professional level, down to patient understandable data. But it can also translate it into different formats such as computer code or clinical codes. And these models can seemingly reason across this, give reasoning as to why these outputs are coming together, wraps it all into a chat interface, making it very, very easy to use, and using any and all of the above to perform its service. But there are some weaknesses. Large language models are trained on a large amount of data, but that data is fixed. And whilst you can ask questions within that data, they can't search the internet unless they're given tools to do so. They're also not very good at doing calculations. These are predictive models, so they're predicting what the next token is. So as a result, they can be quite poor at calculation and maths. They're good at, their translation can be good in many ways, but it's dependent on the training corpus. And as the internet corpus doesn't always have lots of different languages, you can have some problems within there as well in those languages that are less well represented. Now, out of the box, these models are stateless. They cannot remember your previous interactions, and they can be quite forgetful with this. And also, they're not very good at explaining themselves, although they will give reasoning. These are deep learning models and are difficult to understand why they have come up with their answers. These models can lose focus. They have a certain context window, and anything falling outside that window is difficult to be remembered. And also because of how they're trained, they can be sycophantic. They can be influenced by the biases of the input that you put in. And these can lead to some risks. Now, the most obvious risk, or the common risk, is hallucination. These models, by virtue of how they work, will sometimes present information that is incorrect, but presented very confidently. And if you don't understand the subject, that can be a problem. They can be biased because of how they've been trained or the data that they've been trained on, and that can make them unfair when used in clinical settings. For privacy purposes, the data that is within them can sometimes be surfaced, and that can lead to privacy issues. And because their training is often fixed, and you saw how difficult and costly it was to do this, they can slowly worsen, or they can perform less well in different populations. From a copyright perspective, because they're trained on a large amount of internet data, there can be scraped data, and there's a lot of discussion at the moment about whether these data can actually be used for the training of the models. I've told you about the costs. This is a very expensive process to be done, but also in terms of energy and even things like water for cooling data centers. There is a cost to operating these models. And then when it comes to clinical settings, from a regulatory perspective, it can be very, very hard to regulate them. As I understand it now, there are no models, or there are no medical devices around the world that have passed regulation that incorporate a large language model, although much work is taking place in this area. So you understand about generative AI and the training of the models and strengths and weaknesses. So how might they have a role in radiology? Well, a common thing that people do is they test how well these models perform in a radiological setting, and there are multiple papers out there. I have some QR codes here and can share the details afterwards. And in this paper from Bayan et al., it looked at GPT-4 in radiology, and what they found is that GPT-4, one of the latest models, outperformed GPT 3.5 in a board exam, a radiology exam, 81% versus 69% correct. And the larger models perform very well in high order thinking. This was across multiple choice questions. And as a result of this, we're seeing that these models are accelerating in their ability to answer exam questions. But there is some variability in how they perform about this, and they also note that they continue to have hallucinations. Now, this actually limits some of their utility inside any setting, and in radiology in particular. Two papers that I'd like to share with you. This first one was looking specifically about GPT-4 and GPT-4v, which not only incorporates text, but images. And this study comparing the two showed that GPT-4, the text-based one, outperformed GPT-4v. The diagnostic accuracy in this particular case in a musculoskeletal setting was 43% versus 8%. Now, whilst the accuracy of GPT-4 was comparable to that of a radiology resident, it was lower than that of a board-certified radiologist. But what they did find is that if you add GPT-4 to a radiologist, it actually helped improve the quality of those lower trained individuals as well. And it's also important to say that the performance varied across different settings within musculoskeletal. It was variable in this case. Now, bearing this in mind, there's another paper. This paper just came out very recently looking at assessing GPT-4 multimodal performance in radiology imaging. And in that, they looked across an entire week's worth of images from a radiology department. And what they found is that in terms of identifying the modality, they were all very, very good. But this started to deteriorate when they looked at the anatomical region identified or even the diagnosis and pathology. And you can see some breakdowns here that within the different modalities, it was better in X-ray and CT, but worse for ultrasound, both for pathology and anatomy. So it's very, very promising to use these models to try and help with these different processes within radiology, but there remain weaknesses that appear to be corrected over time. Now, I did mention about Doctor plus AI, and this paper from Google last year was very, very interesting, and it showed that one of their specialist models called Amy actually performed very well. And what they did is they compared the performance of a doctor in making diagnoses, which is indicated by the bottom line, and then they allowed them to access the internet, and the doctor's performance raised to this green line, showing they improved. But then when they had access to this Amy model, it improved still further. But what I want you to notice is that when you had Amy performing on its own, it surpassed the test subjects in this particular case. Now, human in the loop, putting a human to check the outcomes, is often used in this situation, and generative AI has some well-recognized risks, hallucinations, for example. Now, they'll often put humans in the loop to check this, but humans aren't very good at vigilance. And in this paper from JAMA, looking at the limitations of clinical vigilance, some of the issues arise is that humans can get fatigued with this, they can get biased to the automation and wave things through, but also people may have a poor understanding of the tool and the processes, making them less critical in assessing what happens. So what are the use cases in radiology if we think more broadly? Where can generative AI help? Well, I think it's very, very useful to take a journey-based approach to these opportunities. And here, taken from a paper, Chatbots and Large Language Models in Radiology, there's a nice little diagram of a patient journey or a clinical journey, starting with the top left with the clinical patient interaction, and then going all the way through the exam and then the follow-up. So where can generative AI help? It can help at the pre-referral stage, helping the patients and the clinicians understand what procedure is happening, deciding on the right modality, and also taking that medical history and summarizing it, producing a concise request. And then at the point of the procedure, helping to select the right procedure, supporting the radiographers and radiologists in this area, providing information and education, but also helping to rapidly review and triage the outputs as well. And then reporting, the thing that comes to everyone's mind, well, it can help with direct and augmented interpretation, extracting those codes from within the reports to help for further analysis, and even helping with decision support. And then on top of this, further research, further analysis, generative AI is believed to have a very substantial role. But I like to say that in these situations, always look to the side of the problem that you're looking at, because I believe one of the biggest impact areas is more broadly looking at the back and middle office and even in people's personal lives, freeing up time and making the bureaucracy and the administration of this work well. So in administration, automated appointment management, maybe through chatbots, ambient transcription for administrative staff, and helping translate through different languages or simplifying the language for different people. But also generative AI can be used in logistics, for audit and professional development, and even in non-work settings in the person's home to free up time for them to concentrate on these clinical tasks. So what's the future of generative AI in radiology? Well, it's interesting to look at how generative AI is moving forward. I've picked 3 areas to look at. Generative AI is getting faster, smarter, and more capable. The faster, more diverse models, including the Falcon LLM series coming out of the Gulf area and the Emirates, the Falcon LLM is extremely performant and performs very well in different languages, and critically is doing a fantastic job of being an open model, allowing people to develop on top of it. And then specialist models, models that have been taken and fine-tuned further, such as the Harrison AI announced last week, is achieving 51 out of 60 in FRCR 2B Rapids exams. As yet not passed through regulation, but very important. And then you've got the addition of video and voice. These models are multimodal capable. So you've got OpenAI Voice Assistant, and here in the bottom right, you can see a sample of a video created purely from a text prompt using Sora. with all of this, I think there is a lot of interesting technology coming your way. Thank you very much.